Hey gang, welcome back for another worksheet solutions walkthrough. And in this video, we're going to be going over the worksheet, fun with functional groups, and a splash of common naming. If you're new to worksheet solutions walkthroughs, they go a little bit like this. There's a worksheet on jOeCHEM. You probably watched the fun with functional groups video as well as the common naming video. You're looking to practice those new skills. You go to the worksheet, you do the worksheet, you look at the PDF solutions that I provided, and maybe you just want to make sure you're doing it right. Or maybe there's a problem you didn't quite understand. That's why you're here. In this video, I'm going to be doing the worksheet, or you'll be doing it as I'm doing it. Either way, we're having a good time. We're going to be doing the worksheet, and we're going to get some answers and see them explained. Let's do it. Okay gang, so in problem 1, we're easing into this worksheet. I've given you two structures. This is aspartame and this is aldosterone, and all I'm looking for is, the point of this problem was just label the functional groups. I promise you on your first exam there's a high chance of you just getting a problem just like this. You'll get a big structure and all you're asked to do is label the functional groups in that structure. Easy points if you've done the little bit just to memorize them, and I know I don't like memorization either, but this is free points on your first test. Plus, if you aren't able to, look at something and identify functional groups off the bat, it's one of those things that might slow you down later on in OCHEM. So just do your, put in the due diligence, the time, just memorize them and snatch up free points. Okay, so in the first one for aspartame, let's take a look. So you can see right here, I'm seeing a carboxylic acid. I'm going to abbreviate these, carboxylic acid. Then moving along, I can see right here, I have an amine. Now careful, I feel like the one thing that can maybe trip you up, and we're human, right, is with amides and esters. So be careful. Don't just look at this and say, oh, that's an amine as well. No. Be careful. Whenever you see kind of an oxygen and a nitrogen embedded in a chain, or maybe on the end of a chain, if you see a C double bonded O nearby, take a pause and just make sure you're identifying it correctly as maybe an amine or an ether, or maybe it needs to be an amide and an ester, right? So right here, I see amide, and if you're saying, Joe, it's amide. I used to say amide. I've heard a lot of professors say amide. Do whatever, I guess, gauge your audience, right? See, pronounce it however you should in the room you're in. Okay, so then right here, right, not just an ether, but this is an ester. And then I've seen this identified, that's why I threw it in as an example. You see a benzene ring, I've seen in different circumstances people have this as a functional group labeled aromatic. If that's not a thing with your current course, don't worry about it. I just threw it in here. Okay, moving down below. So we got this spaghetti monster. Let's start from the right this time. Now, this was me trying to be sneaky, but you can see right here, it almost looks like an ester, like up here. Or, sorry, more like a carboxylic acid. I should correct myself. But there's this extra carbon in here. So this is actually just an alcohol. And then this is just a ketone, right? Because it's a C double bonded O in the middle of a chain, right? We can call these carbonyls as well. Any C double bonded O functional group, you can identify the C double bonded O as a carbonyl. So this is a ketone. So then over here we have another type of carbonyl, but this time it's terminal. Terminal meaning on the end of the chain. So this is an aldehyde. Over here, just another alcohol. And then down here, we can see a ketone. Sorry, I'm trying to write this not on the side I'm usually writing. And then over here, we just have a double bond. So we can just label this as an alkene. Okay, so again, like I said, gang, there's nothing complicated going on here. However, if you just don't have the information in your noggin, you won't get free points. You'll unfortunately lose out on some low-hanging fruit. Okay, that's problem 1. On to problem 2. Okay, gang, on to problem 2. So just like functional groups, another thing that never goes away in OCHEM, not gonna be the last time we say that, is common naming. Now, make sure, again, it's not the sexiest, coolest part of organic chemistry. You're not gonna learn this and then go to your friends and be like, look at this cool stuff I learned. Probably not. However, we need to make sure we are solid with our common naming fundamentals, because it's going to help you with naming IUPAC structures. And again, further down the line, you will continue to learn naming depending on your teacher. However, you are going to want to know how to identify substituents in structures and things like that. So you got to trust me on this. It's boring. Put in the time. Learn how to do it. Okay, so real quick, we have 9 examples here. We're just going to rip through these. So remember, the first thing is kind of count, how many carbons do you have, right? That's going to, determine whether we're doing like methyl, ethyl, propyl, butyl, or some variation of those, right? If we, butyl and propyl, right? So in this first example, we have 1, 2, 3 carbons, right? Cool, so we're going to do something with propane, and we have an alcohol. So this is going to be some type of propyl alcohol, but it's not just regular propyl alcohol, because propyl alcohol would just be 3 in a row with the OH on the end. We are in that middle position, so to, illustrate that to somebody, we would say this is isopropyl, YL, and then the group that's attached, and that's an alcohol. So isopropyl, alcohol. Okay? Moving to number 2. We have 1, 2, 3, 4. We have a bromine on the end, and we're just in a chain, right? Nothing special here. So you can say this is YL, butyl bromide. IDE, right? Because with the halogens, we have to add that IDE ending. And if you're, depending on who your teacher is, your instructor, this could be N-butyl bromide. So just the N just kind of means like, this is an alkane. So N-butyl bromide, but this is optional. So butyl bromide, they're equivalent, they're the same. Moving right along. Okay, so luckily we kind of see the same thing going on here. So we know this is also going to be isopropyl because it's 3 carbons, and we have a substituent attached to that iso position. This is going to be isopropyl. And maybe the hardest part about this is spelling fluoride correctly, but it's Fluoride. I actually remember getting this wrong in the test because I spelled fluoride wrong. Was super annoying, but wasn't my call. Moving on. So down here, 1, 2. So 2 carbons. There's only one way to attach something with 2 carbons. So this is going to be, right, it's an ethane derivative. So ethol and then chloride. Remember that. IDE ending for the halogens, for the halides, if you will. All right, so now over here, something interesting. We have 1, 2, 3, 4 carbons, but it's not like butyl bromide right above it. We're in one of the interior carbons, not one of the terminal carbons. So remember, the little prefix we use, the way we can, demonstrate to someone, hey, this isn't just regular butyl chloride, is we say this is sec butyl chloride. So it's sec with a hyphen into, how many carbons there are. So, right, because this is a secondary carbon, right? Remember, we can identify carbons, their degrees, by saying, oh, like this carbon is attached to 1 other carbon, so this is a primary carbon. Well, this carbon is attached to 1, 2 carbons, it's a secondary carbon. So you can see, it doesn't matter if this chlorine is attached here or here, that they would be equivalent structures, but they are both secondary carbons because this carbon is also attached to 1 and 2 carbons. So sec butyl chloride really means secondary butyl chloride, but sec butyl. Okay, moving right along. Again, we have 1, 2, 3, 4 carbons, okay? So remember, we are in the isobutane conformation here, right? We're not regular butane. We are isobutane, and we've attached something on one of these 3 positions that are all equivalent. So this is just your regular standard isobut, YL, isobutyl, and then alcohol. Okay, nothing to it. Down here, super simple, 1, 2, 3, in a row. Name it how it looks, propyl alcohol. And if you want to, you could call it N-propyl alcohol, up to you. Now down here, we are very similar to what we have up here. So we are in the isobutyl territory, right? This is isobutane, because 1, 2, 3, 4, it's just drawn a little crookedly, but something's attached, right? And very similarly, we have a way to kind of distinguish which carbon it's attached to, this bromide, that is. So this carbon in the middle is attached to 1, 2, and 3 carbons. Remember, that means it's tertiary. So we have the option of naming this tert-butyl bromide, Or if you want to be a cool cat, T-butyl bromide. I prefer T-butyl bromide, less letters, a little lazy, up to you though. Remember, if you're still struggling with why that makes sense, we can use the sec-butyl when we're just straight chain butane because there's only secondary carbons, right? And if we want to designate that we're not just attached on these terminal ends, the terminal carbons right here, the special interior ones are secondary. That's why we use sec-butyl. Now, in the case of isobutane, right, just any of these primary carbons right here, we can just say isobutyl blank because that means we're just attached on the end, if you will. However, we have that special tertiary carbon on the interior. There are no tertiary carbons here, so using tert would never get confusing. Same here, there's no secondary carbons. So that's why sec works perfectly for the 4 carbon straight chain. However, sorry about that. Sec works perfectly for the 4 carbons in a row, and tert works great for the iso situation. And last but not least, you can see we have just a similar look right here. It's 1, 2, 3, 4, 1, 2, 3, 4. We're just attached in a different primary carbon. This is going to be isobutyl iodide. Okay, enough with the common naming. We have, I believe, it's going to be an acid-base section. Let me just check that. Yeah, throw back to acid-base. Why not? It's been a minute, right? So, problem 3, let's finish strong. Okay, gang. Problems 1 and 2 were absolutely in line with the title of this worksheet. However, I snuck a little bit of acid-base stuff on this worksheet because I just wanted to make sure our fundamentals were strong. It's been a little bit of time since we emerged from acid-base basics with our brain fresh of acid-base knowledge. So I just wanted to make sure it's still there and it's fresh because we'll need it very soon. Okay, so we have 3 acid-base equilibria. Remember, right, in each of these scenarios, it's not like this is going to this or this is going to this. It's not static. It's not start and stop, reaction start, reaction finish. It's reactions going in both directions, but there's one direction that is occurring more and is favored than the other. So we need to figure out which direction, right? So we will identify which side of the equilibrium is favored in each of these scenarios. And then I have a little bit of extra labeling that I threw in. And that's kind of why I wanted to do this. I wanted to make sure that this terminology is fresh, okay? So in A, remember, we need to pick the side that is favored at equilibrium. We need to think, remember, we need to think about which side is more stable, right? So in this scenario, in the past we've been doing negative charges. This time we have a positive charge. So let's kind of change our thinking. Who handles or who is better equipped to handle a positive charge? This oxygen or this nitrogen? Now remember, who's more electronegative? If we take a slice of the periodic table, oxygen is the more electronegative atom. So oxygen loves negativity more than nitrogen. If you can kind of think about that in reverse, it's more like nitrogen's more okay with a positive charge if it had to have one than oxygen. So in the case of having ammonium or hydronium have a positive charge, it's actually better for this nitrogen to have the positive charge. This side is more stable. Nature likes that. This is the side that is favored at equilibrium, okay? So now we need to label our, the weakest conjugate base in this reaction. So if we think about that, the weakest conjugate base in this reaction. So the weakest conjugate base means we come from the strongest acid. Now if we think about, there's a saying in acid-base that the equilibrium drives to the weak, and that's just because that means weak means stable in acid-base world, right? So that means nature likes to go towards stability, which means nature likes weakness, if you want to think about it like that. So that means we're dealing on this side of the spectrum, and if we're looking for the weakest conjugate base, you can see on this side, if we were to hypothetically go this way, right, this is acting like an acid, so this is a base, so this is our weakest conjugate base. Let me try and explain that maybe one more time, is that if we're going this way, right, this is our acid, this is our base, because NH3 accepts H+, H3O+, donates H+. So this is the acid, that's the conjugate base. And since this is the weakest side, that means that's our weakest conjugate base. Okay, letter B. So this was an electronegativity thing. Sorry, my pronunciation is not on point today. So what is this rule? Because remember, we have those 5. So we have hydroarsenic acid, and then we have hydrophosphoric acid, right? So remember, I'm going to give you a little slice of the periodic table yet again. We actually did this example in acid-base basics, but this is a size thing. These 2 atoms that are dealing with the negative charge here are in the same column. So that means arsenic, that atom is larger than phosphorus. So since arsenic is bigger, the negative charge that arsenic will have in the conjugate base right here will have a better opportunity to spread itself out around the atom that is arsenic versus phosphorus, which is a bit smaller. So that negative charge doesn't have as much room to spread out. So this is better at handling the negative charge. This side is more stable, aka weaker. We drive to the weakened acid base as far as equilibrium. So now that we've identified the favored equilibrium side, we need to label the strongest acid. So if this is our weak side, this is our strong side, and if we think about it like that means going from here to here, hydroarsenic acid. I realize I probably should have, that's okay, that's fine. It's written a bit weird, I apologize for that. However, that means we are donating H plus from here to here. This is our acid, and because we're on the strong side, this is the strongest acid. Yeah, I apologize. I probably should have done H2AS and H3AS. My bad. Okay, so letter C, last but not least. So down here, I think without even our acid-base rules, we just know that we have HBr and water. HBr, strong acid. Clearly this side is HBr is going to dissociate 100%, donate H+. This is our weak side. We're driving towards the weak. This is the side of equilibrium that's favored. And we need to label the most unstable conjugate base. Now think about that. If stable equals weak in acid-base world, that means unstable equals strong. Okay, so we're just basically being asked, label the strongest conjugate base. So if this is our strong side, and this is the strongest acid, this is our strongest, we can just even say strongest base. Okay? Alright, gang. I hope that if you were coming here for some detailed explanation for fun with functional groups and a splash of common naming, I hope you got it. If you're watching this video, that means you've thrown me a little bit of money and you've supported jOeCHEM, and I appreciate that so much. I'm just honored to be along the ride for your organic quest to crush carbon. And I hope to be here, from now, I hope to be here at the end of jOeCHEM 2, or as long as you need jOeCHEM. But no matter what, I hope to see you all in the next video.